So recording is, I've just started the recording now. Are you there?
Yes, sir.
Good. So let's go back to the notes. So I was doing a revision of what we studied last time. That is a potentiometric transducer. So let me share the screen so that you can enter into the lecture as well and be recorded. All right. So we have the screen now. You can see the schematic diagram of the potentiometric transducer, whereby we see the linear on the left and the rotary type on the right. So that is the way the transducer works. It's a variable resistance transducer actually. And so what you are going to measure will be bonded to the wiper of the transducer, and then the measurand that is capable of moving up and down will be moving the wiper along the length of the resistance. Thus, there will be a change in the current in the circuit, and that is what you are going to take measurement of. Is either you measure the voltage or the current, which will be varying, and then you now calibrate that as measuring the measurand. So that is that. You see the rotary type. The rotary type forms a circular, resistance. They use a circular resistance. If you pay attention to it here on the screen, you see a circular resistance whereby the measurement that you are measuring is actually something that moves in the circular manner, so that the wiper will be bonded to the measurand, and as moving in a circular manner, it moves the wiper around the circular resistance of the transducer. And thus, the transducer will convert that displacement of the measurand into a change in voltage or change in current. And that will be calibrated as measurement of the measurand. That is how the linear potentiometric transducer and the rotary potentiometric, that's how they work. If you look at the notes under 1.1.1 here, you will see the explanation of what I've just given now. It's actually a variable resistor. It's a variable resistor that is used as a transducer. Now, in the other class, I told you that the first practical will be to construct the linear potentiometric transducer. And then I said, because you are not many, we may divide you into two. Some people will construct potentiometric transducer, and then others will construct capacitive transducer. Just one moment. Let me sign out this phone. Okay, so I'm going to sign out the phone so that I use only the computer. Good. So I have only the computer there now. The phone is out so that the echoes will not be coming in if the two of them are working together. All right. So for me, I think you remember that I told you about the first practical, which is based on construction of the capacitive transducer and the potentiometric transducer, the first two practical. Have you been doing anything on that? Miriam, you are also there that day when I said it on the Zoom class. Miriam, talk to me. Do you remember?
Yes, I remember.
Good. So what have you people been doing on that? What have you been doing? Have you researched about the transducer? Have you researched about it? For me and Miriam, you people were in the class that day on the Zoom. Have you researched about the transducer and how to construct it? For me, talk. Let's hear you.
Hello, sir.
What have you done so far on the practical? Nothing. Don't sing. Don't sing. Talk to me.
I haven't done anything.
Don't sing.
Sir, I was not there when you are giving them.
Now you are the
I was
HOC.
not there when you are giving them.
Yes, you have had today, and you are the HOC. You should know how to coordinate your class to have that practical done. Even if it's only to have the idea of what you are going to do. You understand? As you are in different locations now, you may not be able to work it. But if you have researched about it, what you need to do, by the time you come to school, under 2 or 3 days, you can get it done. And then you can have an idea of what you will need to construct it. Maybe it's only 30 naira you will contribute to, or 22 naira. You have an idea, and you discuss that one before you resume school. You understand? Don't sing. So you are the HOC. So try and do that, coordinate that. That's what I want to tell you. All right. So we want to also talk about linear variable differential transformer. I think we mentioned it. Let's have a revision on that one too. Linear variable differential transformer. So I'm going to share my screen again so that you can see the notes. Okay, this is it. So linear variable differential transformer is a LVDT. We have been hearing about LVDT since 21, but we want to look at the principle of operation. We have discussed it the other day, and then you will see the sketch on the screen now. A is the connection of the device. The transformer is made up of 3 coils. The LVDT is made up of 3 coils, and it's a high resolution contact transducer, high resolution. It has 1 primary coil and 2 secondary coils. Now the 2 secondary coils are connected in a special way so that you could have addition of the voltage or subtraction. You could have positive voltage at the output or negative voltage at the output. And then the transformer has a core. The core is capable of moving linearly. If you look at this screen now, you will see displacement and you will see arrow that points to left and right. It means the core can actually move to the left or to the right. As the core moves, then there will be a linkage of EMF produced from primary to the secondary. Depending on where the position of the core is, that's what determines which of the secondary coils, is energized. And that determines whether we are going to have a positive voltage output or negative voltage output. And so that is the way the differential transformer moves. What happens is that the measurand, what we are going to measure, will be connected to the core of the LVDT. And so what you are measuring will be moving, and it's moving, it will be moving the core in and out of the coils. And that's what determines the type of voltage that you are going to get at the output. The AC voltage is supplied to the primary coil. So there will be electromagnetic induction. But the electromagnetic induction that's going to take place will depend on the position of the core inside the coils, so that the magnetic flux from the primary coil cuts either primary coil or secondary coil. Maybe primary coil partially or secondary coil partially or fully, whichever way, is the position of what you are measuring that determines that. So we can have the voltage developed as in figure B. If you check figure B now, you will see the voltage developed. You will see that we have a negative voltage, also a positive voltage. Okay, since phone has disappeared also, remains only 2 of you. His network is not good. All right. I think Fumi and Miriam can still hear me. You are still following, right? This is a revision of what we did before. I want to go to new portion today. Before we go, look at where I put the screen now. This is physical appearance of the potentiometric transducer. The linear type on the left and the rotary type. It's like a potentiometer actually. I use variable resistor. So that's what we have. That's what we have there. So you can see it in your notes as well. Now, The LVDT has this formula that determines the voltage that we generated. If you check the screen now, you see delta V naught is equal to K delta X. Delta X is actually the position of the core. Delta X is the position of the core, and then the V naught is the voltage at the output voltage that is produced. Now, the K is a proportionality constant. K is a proportionality constant. Delta X is the change in position, and that is what is determined by the measurand that is pushing the core in and out. All right. Resolvers. Resolvers. Number 3 of the transducer resolvers. A resolver is a rotary transformer. A resolver is a rotary transformer. And the winding of the transformer is on the rotor. And the secondary winding is on the stator. The secondary winding are set 90 degrees apart. And then an alternating current is applied to the primary winding. So as the shaft is rotated, what happens? When the shaft is rotated, it's able to capture the position of what is being measured, because the voltages on the secondary coil will vary as sine or cosine the angle of the rotor. So whatever you get will depend on the position of what you are measuring. Where what you are measuring is will determine the voltage that is produced at the output of the transformer. So if you check page 7 now, you will see the schematic diagram. You see the resolver schematically drawn. You see the primary coil. The primary coil is the stator, is on the stator, and is able to roll. It's able to move and in an angular manner. And so when it moves, there will be EMF induced into the secondary winding, but we have 2 secondary windings. So it is the position of the primary coil that is moving in angular manner that determines what EMF is produced at the secondary. So therefore, we're going to have voltage produced as a sine or cosine of the voltage applied at the primary. It's a very interesting transducer. It's also capable of measuring angular movement of the measurement. Capable of measuring angular movement of the measurement. Maybe you people should mute your mic. I'm hearing somebody's mic bringing noise. You can mute your mic. Now, in the resolver, the output voltages can be converted by a binary count using a resolver to digital converter. A resolver to digital converter. So, the device combines the circuitry necessary to interpolate the output voltages into angular positions and the analog to digital circuitry required to digitize the results. Meaning that whatever you are going to get from this resolver, you are going to get a digital output. So the device is capable of giving us a digital output, not only analog voltage. It's going to give us a digital output because analog to digital converter is incorporated into it. So when you need an instrumentation system whereby you need a digital output from an angular, measurement, the resolver is very, very applicable at that point. The resolver is well applicable at that point. So that is it. The resolver is a non-contact transducer, unlike the potentiometer. Potentiometer is a contact transducer, but resolver is not a contact transducer. So it doesn't have to make a contact with what you're measuring. So it will not lose accuracy due to wear and tear. So the resolver is a high precision transducer, and then the only limitation is imposed by the analog to digital converter. The only limitation is because of the analog to digital converter that converts the analog voltage into digital currents. So analog to digital converters that is incorporated in the resolver to resolver have up to 12 to 16 bit resolution. Up to 12 or 16 bit resolution. Okay, that's about resolver. Okay, Johnson is back. Johnson is joining again. I think his network is back. All right. Johnson, you are welcome back. Do you have any question on the resolvers? Any question? Johnson, you are back. Miriam. Johnson.
Hello.
Johnson, you are back.
Yes, sir.
It's okay.
Yes, sir.
So let's continue. We have discussed about resolvers. Do you have any question on resolvers? If there is no question, then we'll move on to the next. The next one is optical encoders. Optical encoders. So we want to talk about optical encoders. There is something similar between encoders and resolver. The similarity is that the two of them can measure digital values. They can produce digital results. So analog to digital converter is applied in a resolver. Now, optical encoder can also give us a digital output. It's a digital position measuring device, and it's available in both linear and rotary construction. And how does it work? It works with light. If you look at the name, it's called optical encoder. Optical encoder. When we say something is optical, you always remember that it has to do with light, optics. Optics. So the transducer is able to convert light into electric signal. It's able to convert light into electric signal. And so, how does it do it? If you check the page I'm showing on the screen now, in the notes, that is under 1.1.4, you will see the schematic diagram of how it works. You will see the optical encoder. You see a source of light coming, and then you see a slot, a rotary slot that is applied in between the source of light and a receiver. The receiver is a transistor, it's a light emitting diode or a photosensitive transistor. Light emitting diode, how does it work? When a light is shined at the PN junction, then it will receive photon energy and then it will be forward biased. It will be forward biased. Now, the same thing goes for a phototransistor. If you shine the light at the base emitter junction, then the base emitter junction will be forward biased and the transistor will be turned on. So without getting the light, it will not turn on. The same thing, the light emitting diode. If it doesn't get the light, it will not turn on. So the emitter in this schematic that you are looking at is actually a photodiode. It's all right. It's a photodiode. And so when the light shines, the light that you want to convert into electricity, when it shines, there's a disc, a slotted disc that is rotating. When the disc allows the light to pass, it reaches the emitter and the diode is energized. And then it passes current to the output. Now, when the disc turns to the dark position, then there will be no current. So that we have current coming on and off based on the slots of the discs. As the disc rotates, the light will be alternatively blocked and allowed to pass. So alternately rather, we are going to have on, off, on, off. So if you check the schematic diagram of the output voltage, you will see the output voltage that comes in as a rectangular waveform. Just like when you do 555 timer, you have a rectangular waveform. Now, to convert this rectangular waveform to sinusoidal form or kind of triangular form, we apply a Schmidt trigger. A Schmidt trigger is applied at the output to convert the voltage into a kind of sinusoidal form. So you see the output now, output from the Schmidt trigger that is sent to the detector. The output from the emitter is like a rectangular form, but Schmidt trigger converts it to a rectangular form, from triangular to rectangular form. The triangular is directly from the emitter, while the Schmidt trigger converts that one to rectangular form. And so when you have this rectangular form, it means you can have on, off, like your unstable multivibrator. And that's a digital output. It means you can have 0, 1, 0, 1. You can have 0, 1, 0, 1, which is actually a digital output. So in essence, an optical encoder converts light into a digital output by simple mechanism.